astrophysics, optics, and electronics, we have the talk of Dr. Luis Eduardo Vieira. He is a researcher from Brazil, and Eduardo Tirado will talk a little bit, a resume about our guest. Please, Tocayo, could you
Thank
go
you,
ahead?
Doctor. Today we are delighted to have Dr. Luis Vieira as our speaker. Dr. Vieira in 1995 received his undergraduate degree in physics at Federal University of Santa Maria. After that, in 1998, received his master's degree, and in 2002 his PhD in magnetospheric physics from the Brazilian National Institute for Space Research. At the present time, he holds a permanent position as a researcher in solar physics at the Brazilian National Institute for Space Research. He is member of the Frontiers editorial board, associate editor in stellar physics and solar physics of the journal Frontiers in Physics.
La grabación ha
He is
comenzado.
also a reviewer of international journals like Geophysical Research Letters, Journal of Geophysical Research, the Astrophysical Journal, the Astronomy and Astrophysics Journal, among others. So, let's welcome our speaker today.
So thank you very much for the invitation to present the progress of our research activities in Brazil. And of course, it's a very nice opportunity not just to share what we are doing, but also to explore the possibilities for collaboration with your team there. So what I would like to talk a little bit about our project that we started in 2013 when I returned to Brazil to explore the possibilities to have some kind of a group to develop instruments for solar observations. You know, INPE has now more than 60 years, and we have explored several fields in space physics. But we miss it to have a group in solar physics, at least a group with a strong instrumentation development. So in 2013, we answered a call from our institute to fund projects related to instrumentation, and in that opportunity we proposed our very first instrument that was related to solar physics. We, as I mentioned to Eduardo, we started from a group of theoretists at INPE. No one of us developed instruments before. So in the first moment we proposed to develop a proof of concept instrument to try to estimate the magnetic field at the surface of the Sun. So this was our starting point at the INPE for the development of instruments for solar physics. During the seminar I will talk a little bit more on how we developed these ideas, and now we are at the point to propose a space mission, which is the Galileo Solar Space Telescope. So here I will talk. I will give a small overview about our ideas. Let's talk a little bit about the underlying basic scientific questions that we are going to explore or propose to explore during the mission. We also state our scientific objectives, a little bit about the mission concept, the instrument development, and also I will conclude the basic ideas that we're exploring here. So first of all, it's important to let you know that, of course, that we are very interested to have the Galileo because of the scientific objectives, But for us, it's also important to take into account that such kind of project is important to our institute and to our space program in Brazil. Of course, that we are aiming to develop and contribute to understand the effects of the sun on our nearby environment, that we are also trying to develop high-resolution imaging capabilities that can be also employed to different activities, not just for solar physics, but also for observation and other activities related. And from this information, we would like also to understand of course, the effects of solar activity on Earth, and regarding to the development of technology, would like so to improve and contribute in the fields of optics, electronics, data processing, and of course create new opportunities to the Brazilian industry, that it's not just related to the space activities, but also to other activities related to our industry. So, summarizing, we think the GSST, both as a mission with a very specific case in solar physics, but also a mission that can help to promote our national industry in space-related activities. And of course that you know more than me that we are not alone in this challenge. In fact, several colleagues and groups at NASA, ESA, JAXA, and other space agencies, they are working in missions both to observe the sun and the environment near our planet and other planets. So we are willing to contribute to this international effort, not competing with the other groups, but by providing complementary information and data. So in this context, we already have at the INPE a specific space program that is meant to work in the radiophysics and specifically to provide to decision-making entities the information needed to operate space activities that depends on the conditions of the space environment. So at the INPE we have the Embrace, which is a center designed to investigate our space weather, specifically space weather in our region, which is related to the magnetic anomaly of Atlantic magnetic anomaly. So we have teams exploring deeply the ionosphere, the upper atmosphere, radiation belts, as a whole the inner magnetosphere, and of course the drivers from the sun to the interplanetary medium. So our proposal is in this context of the Brazilian space weather program by contributing to our program and also providing information to the international community. So as I mentioned, we are not interested to provide the same information that it's already provided by other teams, observatories, but to complement this information. And what we can see here in this movie are very nice images from SDO, from NASA, but we have also several other observatories. And what we have here is a large number of parameters, information that can be extracted from these images and observations. But we have one information that it's not systematically captured now, which is the magnetic field in the outer regions of the solar atmosphere. We have very nice observations for the magnetic field at the solar surface, but we still have to provide more constraints on the intensity and the vector or magnetic field vector out of the surface. That could, of course, help to constrain magneto-hydrodynamic models for the chromosphere, transition region, and corona. So our idea is to really provide information in a complementary way to other observatories. Of course, that we can state that the science that we are aiming is of the great interest for the solar and stellar communities. Our objectives are technologically challenging, and will lead Brazil to acquire new technology capabilities for space activities. We, of course, as all other nations, we are willing to join the select group of nations that are capable of solar observations, employing space-based platforms. And as I mentioned before, it's really a great opportunity for international collaboration. So what kind of scientific questions we may address with this, and we are willing to address with this observatory? The first one, which is the one that it's of a great interest for our society in Brazil, which is to untangle the effects from natural and anthropogenic drivers of climate change. So understanding how the sun changes in scales from centuries to millennia is very important. But first of all, we have to understand how the sun evolves in short time scales. Well, together with all of this information related to the variability of the sun and its impact on our climate, we really want to understand and contribute to the understanding of the basic and fundamental physical process that are at work in the sun. And one of these, of course, is the solar dynamo itself. We would like to contribute to the understanding on how the external regions of the solar atmosphere is heated. So what kind of process lead to the heating of the outer layers? And of course, as we are going to have our observatories in the vicinity of our planet, we would like also to monitor parameters in the Earth's magnetosphere. I mentioned the problem of understanding how the evolution of this magnetic field, solar magnetic field, may affect Earth's climate. The basic idea behind is that the magnetic activity modulates the solar irradiance that reaches the top of our atmosphere, and of course, this radiation is the main power source for our planet, and this energy is redistributed on our atmosphere, land, oceans, and eventually it's irradiated to the space in such a way that we should be in a balance because of the change that we are producing in our atmosphere since the beginning of the industrial age. We have an imbalance, and this imbalance is leading to the change in the atmosphere and the ocean patterns. So we would like to contribute to the understanding of this field by measuring the variability of the irradiance at the top of the Earth's atmosphere, as well as measuring the solar magnetism. And just to make our case, of course, that we have several observatories during the last 4 decades. Here we have in this plot the total solar irradiance, the irradiance at the top of Earth's atmosphere, measured by several observatories. And we can see that the measurements now converge to a giving a range of variability, but it's still challenging to understand the variability of the total solar irradiance on long time scales from centuries to millennia, based on the information that we have for these few decades. So, as better as we understand the variability during the solar cycle, specifically during the solar minima, we can improve our models for the long-term evolution of the solar activity, specifically for the total solar irradiance, which is one important parameter for modeling the evolution of the Earth's atmosphere. Here, just to mention that we have a plot of a reconstruction of the total solar irradiance for the Holocene, the last 11,000 years, and we can see that we can have states of low activity, which means low solar irradiance, and states of high solar activity, which is close to what we are now. And so this, of course, produce variations in Earth's climate. So to really have a quantification of the changes that we are observing now, we have first of all established the baseline for solar variability. And as you know, everything that we are measuring in our nearby space is related in the end by the evolution of the solar dynamo. So it's really a complex chain of events that start at this solar interior and propagates through the several layers inside the sun and through the interplanetary space and interacts with the several planets. And when we talk about measuring the sun employing a space-based observatory, it's because we really need to go to the space to have access to some windows in the solar spectrum that are accessible just from space. And of course, that from these observations we can investigate different layers of the sun that depends on the wavelength, and also different phenomena from the small scale evolution of the solar activity to explosive events such as flaring activity. One important point that we would like to explore during our investigation employing the Galileo Observatory is the propagation of the waves in the solar atmosphere. So, as I mentioned before, looking to different layers at the sun. And for us at the INPE, it's really important and interesting to investigate the conditions in the inner magnetosphere, specifically the Earth's radiation belts. So we have an interest of understanding the variability, because of course we have several spacecrafts in this region, but also because of the precipitation of particles in the upper atmosphere related to the South Atlantic magnetic anomaly. So the objectives that we define from these open questions that we are trying to explore are the evolution of the magnetic structures in the outer layers of the sun, the relation of this, the variation of this structure with the variation of the irradiance. So trying to contribute to the understanding of the solar influence on Earth's climate. And the last one, the understanding of the Sun in the geospace. So basically, for the main objectives, we are willing to build cameras or optical instruments to image the Sun in the visible and in the ultraviolet, which means that we can try to access the variability of the magnetic field in the regions out of the solar surface. This is our long-term project planning. We started, as I mentioned before, in 2013, and in that moment we start to develop a proof of concept for a magnetograph that we already concluded. We later started to install this instrument in a ground observatory that we may so test several aspects of this instrument. In 2017, we had the opportunity to start our space-based observatory. It was a very nice opportunity because INPE created at that time a facility to explore and study the initial steps of space missions. And this engineering facility helped us to define the very basic concept for the Galileo Solar Space Telescope mission. And for our very long-term planning, we would like to have not just one spacecraft, but if possible, a family of spacecrafts. And of course, that one very interesting and challenging situation would be to have the observatory out of the plane, of course, to explore different regions of the heliosphere. So let's talk a little bit about the concept of how we can measure the magnetic field. As you know, now we are not able to really deploy a magnetometer in the solar corona. So the way to estimate the magnetic field is employing a proxy. And the proxy is based on the Zeeman effect, which is basically a breaking in the symmetry of the region that we are trying to observe in such a way that you have a splitting in spectral lines sensitive to the magnetic field at the source. For example, here in the bottom on the right, we have an image of a sunspot, and if you look through a slit and the diffraction grade, we can have the spectra for this region, for this slit, that is what we have here on the right. So in this region near the sunspot, we can clearly see some change in the spectra, and this change in the spectra is exactly due to the Zeeman effect. So what we have to do so to try to estimate the magnetic field is to investigate changes in the spectra in these lines that are sensitive to the magnetic field. But you can see here that we may need a really sensitive instrument to distinguish the spectra. So we can also employ the polarization as a way to distinguish the vector magnetic field. So the pipeline to really compute the magnetic field at the solar surface or in the outer layers is capture the light with an instrument, a telescope for example, scan the state of the polarization state of the light, scan the wavelength, and acquire the information employing a camera. At this point, we are working with hardware. From that, but it's not enough. You really need a second to work with the data to explore the Stokes parameters, employ inversion models from these observations of the Stokes parameters, and in the last moment we can estimate the magnetic field and other plasma parameters. And how people do it? If you are trying to observe a region, we can employ some imager, as we are proposing to do. And here we have one example of what they are doing to observe, to estimate the magnetic field at the solar surface at the Solar Dynamics Observatory. So the basic idea is that you have to scan in wavelength and both in depolarization state. So these images combined can lead to the Stokes parameters, and in the end we can here we have the Stokes parameters for different wavelengths that comes from the previous image that I showed before, and combining this information we can invert the problem and extract from the Stokes parameters the information for the intensity and the angles of the magnetic field. And in the end, if you are looking to the solar surface, we can produce maps such as this. Of course, that we are not just interested to reproduce the observations for the solar surface, but also to estimate two regions for the outer regions of the solar atmosphere. So let's talk a little bit about the concept of the Galileo Solar Telescope. I mentioned that we did some preliminary analysis together with the INPE's engineering coordination. So the idea was, first of all, identify the system drivers, and critical requirements were identified. Basically, we understood that the optical payload architecture, the orbit, and the way that we work with the scientific data at the ground are the key elements for this mission. Regarding the optical payload architecture, we explore several different configurations. For orbit, we explore both low Earth orbit and geosynchronous orbit, and also we explore different possibilities for acquiring and distributing the data. In the end, we understood that we needed two telescopes for imaging the sun solar disk and one for the high resolution. The high resolution would be related to two instruments, one to measure the magnetic field in the visible and the other in the ultraviolet, while the two telescopes imaging the solar disk as a whole would work individually in the visible and the ultraviolet. So we designed the imaging payload that we would need for these observations. So basically, as I mentioned before, we'd have two telescopes like this one on the left, upper left, imaging the solar surface and the outer regions, and the same for the high resolution telescope, imaging in high resolution both the surface and the outer regions. In this analysis, so we defined some requirements for the cameras, several parameters, and the configuration of the the telescopes needed, as we have in this table here. So based in this information, we design the optics of the telescope. So here we have the two main channels, in ultraviolet in blue, and in red we have the channel for the visible, and you may notice here a channel in orange that it's not a scientific but a technological camera that would be designed to keep the tracking of small features and provide the stabilization of the imaging system. The same analysis was done to the full disc cameras. And here I would like just to show you the high resolution telescope would be something like this one that we have installed here in the parking place in our institute. That we are deploying, as I mentioned, to test some of the instruments that we are developing. And here also, just to mention that we did the same analysis for the full disc camera, designed the optics and the mechanics. Regarding to the orbit, we analyzed the two possibilities. Both are feasible, geostationary orbit and not geostationary, geosynchronous, and a low Earth orbit. Both of them can be employed. Of course, that there are major difference between the approach for each one, with the low Earth orbit much less expensive than the other one. We also designed the possible satellites for both solutions. So here we have the basic parameters for both of them. So of course that it would be much more expensive to deploy at the geostationary light orbit. We are also developing, as I mentioned, several instruments. Some of them may or may not be deployed together with this mission, but we are exploring these possibilities. One of the instruments that we are trying to develop is a spectropolarimeter based on volume holographic narrowband filters. The problem is that it takes a while to scan the spectra and the polarization states. And as you know, the solar phenomenon occurs in several different scales. And the very interesting one related to solar flares, for example, they occur in a time scale short than the time needed to acquire the information to reconstruct the magnetic field. So our idea employing these holographic filters is to acquire simultaneously images in wavelengths nearby the line of interest, and that would allow us to reconstruct in high temporal scale cadence the magnetic field. So this is a very interesting field that we are exploring. For this development, we are also not just recording the holograms, but we are also growing the crystals needed for this activity, which is by itself a very interesting project. So here you can see the crystals that we are employing to record the holograms, but here on the right you can see the ovens that we are working to grow the crystals. And also related to, so here we have some results of how we can, how it works. So basically, these crystals and these holograms work as very narrow band filters that depend on how we record the holograms. We can have a different spectral and angular selectivity for the images. And combining all of this information, we can build a spectral polarimeter. And it's not just regarding the next step is combining what we know about optics with artificial neural networks, and both in a digital way, but also in employing our optic processing. So our idea in the end is to have a real magnetograph just based on our optical system. So I will not explore in details, but we are already making some progress in this field. Other instrument that we are developing is broadband radiometers. As I mentioned, one of our objectives is measuring the total solar irradiance, and to develop these radiometers, we need to develop also some materials. These radiometers, they are based on the idea that the changes in the sensor element are due to the exposition of this element to the solar radiation, and the basic change would be in the temperature of the element. So the element should acquire as much as radiation as possible. At IMP, we had the opportunity to develop such materials that are meant to capture most of the sunlight. And these films are based on nickel phosphor, as well as we are working on carbon nanotubes. For the radiometer, we are also developing different technologies. For example, as I mentioned, the basic point is to measure the temperature. To do this, we are, instead of employing a thermopar or other traditional components employed to measure difference of temperature, here we are trying to develop an interferometer so we can measure the temperature by measuring the changing phase of the interference patterns. And if you allow me to talk a little bit about the progress of our project, here we have an image of one of our first meeting about 10 years ago, when we got together with people from IMP's engineering coordination, who helped us to organize the project from in the beginning. So we really made a lot of progress because of their help at this point. So at this moment we decided to exactly how we would proceed, and it was at that moment, about 10 years ago, that we decided to build the proof of concept spectropolarimeter that could help us to have some know-how in the development of these instruments. So with our colleagues, we developed the whole architecture for the instrument. We designed the optics for this proof of concept, including the major components for the polarization analysis that I mentioned is the critical one, and also employing a Fabry-Perot etalon to scan the given region of the solar spectrum. From that moment, we started to work in the mechanical design, and of course the design of the filters needed to reject solar radiation not employed for this analysis. From the optics, we started to design the mechanics, and in parallel, we implemented a laboratory, an optical laboratory to build the instrument itself. If we have some colleagues from there that already visit the INPE, so they know that we have several laboratories that can be employed to measure in detail the optical properties of the components. We design equipment to assemble the optics. Here we have one example of the integration of the system with colleagues from the Brazilian National Laboratory for Astrophysics. We aligned the instrument. Here you can see when we started to build this and align the instrument. Here's one of the first versions. Here you can see the liquid crystals employed to the polarization analysis, as well as a Fabry-Perot on the left. Cameras to acquire the information. Here it was one of the first time that we got the sunlight inside the instrument. It's interesting to mention also that we developed the software and so on to acquire the images. Here I will not get in details, so basically we are employing a Fabry-Perot to have a very high resolution scan of the line that we are interested. Here we have one of the first images that we acquired in 2018. We can see the two lines that we are focusing now, two iron lines that are sensitive to the magnetic field. Here on the left we have one of the first observations. I scanned through several wavelengths in that region. Here we have a comparison of the MDI with our observation inside of the laboratory. So we can see, not that it's not exactly the same information, but we can see the same structure that we in both images, the one from SDO and the one that we acquired in our laboratory. So it was our basic idea of the project and the concept. We would like to have this progress going to the next step. We learned how to build this instrument, and we would like in the next steps to deploy first in the observatory nearby the spectropolarimeter, and if you have the opportunity to go on with the space mission. So one important point that I have to mention about the space mission is that at this point it is being analyzed by the Brazilian Space Agency. It's in the portfolio of our institute, and we a bit about our project, and of course we are open to questions, and not just now, but if you would like to contact later by email or any other communication way.
Thank you, Luis.
So Eduardo,
si quieren hacer también alguna pregunta por el chat, en español pueden hacerla. Si alguien gusta hacer alguna pregunta o comentario, adelante.
Oh, feel free to. It's very important to exchange the ideas and.
Yes, 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 of course. Also, the possibility of further collaboration is an
Exactly.
important point. Yes.
I have not mentioned, Eduardo, but we have here at INPE a postgraduate program that we have students from the master's and doctorate levels, and it's possible to exchange students with college institutions abroad. So several of our students, they go and visit other institutions, collaborate with different the analysis of different data, also help
Yes.
to develop instruments together. So it's really a nice opportunity to such kind of collaboration, both to in this program we can send our students abroad, but also host the students from other institutions here, which would be a very interesting opportunity, for example, to collaborate with your group. No?
Yes, yes. An opportunity of collaboration. ¿Preguntas? ¿O comentarios?
Eduardo, maybe I could ask a couple of questions.
Yes, yes, of course, Sergio. Please go ahead.
Well, first thing, thank you very much for the presentation. It was a quite impressive amount of work that you presented. I was wondering, how long have you been working on the design and the construction of the telescope? And are your students from the space science program, the graduate program, participating in the construction of it?
Oh yeah, so we are working in these projects related to the Galileo for almost 10 years now. And during all of this time, we have the permanent position people at the INPE working in this project. But most of the people working, they are graduate students from our master and graduate and doctorate program. We have also postdocs working with us. For example, the project that I mentioned about the holograph filters is a PhD project from our colleague Felipe Tavares. The development of the interferometer for the broadband radiometer is a project from Adriane Barbosa. The position of the thin films was also a PhD project from Franciele Carlesso. So we have several projects related to the instrumentation, and of course we have theoretical or data analysis projects that we have also in our team. So students work with radiation belts, with waves in the solar atmosphere, computation of the magnetic field. We have also collaboration with colleagues from the computer applying program at the INPE for example, modeling and machine learning studies. So there are several opportunities that we could have together with our colleagues both inside INPE, but also in collaborating institutions nearby INPE. We have several universities that are contributing and can contribute in these studies. No? It's a very interesting question because all of these projects, they help us not to acquire technology, but also to get the formation of human resource in Brazil, no? And having the opportunity to collaborate with institutions abroad, it's very helpful to bring some know-how to Brazil.
Yeah, thank you. That is very, I guess, inspiring that you have most of the work being done by your students, graduate and postgraduate students. When the data starts being available, how will this be made available to other institutions? Will this be through joint agreements?
We, as I mentioned, we have this space weather program here in Brazil, and our idea, our policy at INPE is to make all data available as soon as possible. So we are planning to have the data available at different processing levels as soon as possible through our space weather program. So we are really, most of the data that we have available at INPE, they are made available at this system that we have. So we are planning to follow the same procedure and deploy all images that we get, or the magnetic field and particle data available through this internet site. I can send you later the link I sent to Eduardo, and then he could share with you the link for the data that we already have available.
Yes, thank you very much. We have a couple of students that are working on space weather, and they and the teams that they participate with would probably be quite interested in beginning to explore how to use the data and then establish contact with some of INPE's or other Brazilian researchers.
Yes, I think that it's really a nice opportunity to start a collaboration, and both Eduardo already visited us, no?
Okay. Thank you, Sergio.
Yeah. Eduardo, I have a question.
Yes, please, Miguel. Go ahead.
Yes. Well, the question, many things that you have mentioned, Luis and Sergio, are very important, in particular also for Mexico, which are in the early stages of space program developments, no? That's something I would say. And an important aspect of all of this is how much money do you need to have a GSS mission? How much are you expecting to spend? And what are the sources of that money?
So the one thing that I have not mentioned this time is that we had this study for the concept of the mission. And recently, last year, INPE tested one platform that is meant to be a platform for multi-missions. It was the Amazon 1 satellite. So it was a very successful mission that most of the design was made at INPE. And INPE's engineering proposed to employ the same platform to Galileo. So we have now a very interesting constraints on the cost of the mission. So the cost to launch the mission was about $25 million just to launch. To develop the operational model, all facilities in the observatory was about $40 million. And we expect to have at least the same for the payload, to develop the payload. The source of this research, we expect to have most of the Brazilian space agents that pay, for example, Amazonia 1. But for some payloads, we expect to collaborate with foreign colleagues in such a way that we can speed up the process, because it takes a lot of time to have the payload qualify and in a high TRL that could reduce the risks for the mission. So we expect to share this cost with the colleagues from foreign teams. And the timeline, it depends a lot. It's not so different, I guess, from Mexico or any other country that are trying to get into the space activities. It depends a lot of our political situation and the overall economy of the country. If we have all conditions, it would take about 42 months to complete the whole mission. If we have the resource available in a given point. So this is our estimate to have the mission ready to be launched. One important point is that at INPE we have all facilities to test the satellites. So it's going to reduce a lot the costs for testing and so on. And we don't need to move the satellites from one place to the other to test. This reduce a lot of time. So this is more or less our strategy. Now we are following the steps to have all approvals inside the space agents, and it may take up to 1 year to have the approval. On the other way, we have already applied for the funding both in the space agents and other source.
Yeah. Thank you very much for your answer, and thanks again for your talk.
Well, thank you very much, Miguel.
Thank you, Miguel. Another question? Please remember you can write at the chat in Spanish if you prefer.
Yeah, and of course, if you have questions that you prefer to email us, also feel free to.
Okay, thank you, Luis. More questions or comments? Okay, it seems we have no more questions. Luis, thank you very much again for your talk. Very interesting, lot of work. Really, it's a huge amount of work. Thank you,
Well, thank
and
you.
thank you all our colleagues and our students from City for attending this talk. Bye, everybody.
Thank you very
Eduardo,
much.
Bye.
thank you. Let me
Bye.
just
Thank
take
you.
the
Thank you,
opportunity
Luis.
to advise that you are going to give us a talk in 2 weeks, no, Eduardo?
Okay, Luis. Yes,
So
yes,
I
of
just
course.
confirm that it's okay.
Yes, okay. We can arrange it. Thank you.
Thank you,
Thank you for
Luis.
inviting me. Okay.
See you. Have a
Okay.
nice
See you.
evening.
See you.
See you.
Bye
Bye.
bye.
Bye. Bye, everybody.
See you soon.